So far this semester, we've been focused on describing changes in motion, and this is a part of physics that we call kinematics. And in that sense, we've been thinking about position. More importantly, how's that position changing? So, displacement, velocity, and acceleration. We have not been really focused on why is the object moving the way it is, or why is its motion changing. We've just been describing those changes in motion in terms of displacement, velocity, and acceleration. Now we're going to shift our focus to what we call dynamics. And in this section, we're going to now start thinking about, well, why is the object moving the way that it's moving or not moving the way that it's not moving? And so, again, this is called dynamics. And so, to really understand that, we're going to need to think about forces. Forces are going to help us understand the whys of our motion. So real quickly, I want to go back to just looking at, I showed something like this at the very beginning of the semester, probably the first day, and thinking about just how the class is set up, right? So in this class, a big focus that we want to be thinking about is how do we approach problems from a really high level, right? We don't want to focus on just kind of finding some very specific equation. We want to start at sort of the big governing equations and then work our way down. And so in this class, we have kind of four really big approaches to how we're going to solve problems. So the first was constant acceleration. And so what I mean by that is we can do a constant acceleration type of problem. And for that type of problem, we know we are working with an interval or a constant acceleration. I can have my interval diagram. And then we have our three equations, right? Our three starting equations that we can work with. So we've done this. We're moving on to our next piece. What we're doing now is what I call second law approach. So in this section, we're basically going to be using Newton's laws of motion to help us solve our problems. And so with second law equations or Newton's law equations, we're going to be using the equation where sum of forces is equal to mass times our acceleration. This is going to be our starting equation that we're going to work with for the next couple of weeks. Now we're going to move on to energy, and energy is going to be a very different type of approach. But again, we're going to have a very simple kind of starting equation. So I'm going to say delta E is equal to some work other. And then we'll move on to momentum, different approach. Also very simple kind of starting equation. We're going to say delta P is equal to J external. And so when we think about physics kind of from this high level and thinking about, am I going to approach this problem using second law or conservation of energy or conservation of momentum, it really allows us to think about any problem with any level of complexity, because I can start up here with this very general equation. And what we're going to do is I like to call it unpacking, right? We're going to unpack these very simple equations into much more complex things that focus on the situation that we are specifically working with. So we've done constant acceleration. Another thing I want to mention and highlight is that we are not done with constant acceleration. So constant acceleration shows up in every single one of these other pieces. So we're going to still be doing those types of problems. We're just adding on to them and allowing ourselves to work with more complex situations. So don't forget about all your constant acceleration stuff, because we are still going to be using it. All right, so what I want to do in this video is really just give an introduction to forces. So what are they? How do we work with them? And in the next video, I'll talk through some different types of forces that we will be using in this class. So first, most generally, we can describe a force as just a push or a pull. That's our kind of most simplest way to describe what a force is. Forces are also always going to be interactions between two objects. So it's going to be very important that we always can identify an object and an agent. So every force we can describe should have something that the force is acting on. That's going to be the object. And something should be doing the acting, right? That's the agent, the thing that is doing the force or exerting the force. So when we are thinking about our different situations or scenarios, we are going to be focusing on the perspective of the object. So we'll define the object, and we want to think about all of the forces acting on that object. And we want to remember that every force we say is acting on that object has an agent. We should be able to identify what is doing the force, or what is creating or exerting the force, the push or the pull. Forces can be either contact or long range. So if we classify all of our forces, we can put them into one of these two categories. Contact forces are exactly what they say. So these are forces that happen when there is direct physical contact between the agent and the object. So most of what we will work with in this class are going to be contact forces. So things like if you're pushing a box across a table, right? You're going to physically, your hand is physically going to make contact with the box. That would be a contact force. The force of friction of the box with the table is a contact force because the box is touching the table. So again, most of what we're going to work with in this class are going to be contact forces. Long range forces are forces that act without direct physical contact. So these are forces like the gravitational force is one that we will be using in this class, and then also all of our electromagnetic forces. So those are also long range forces. In this particular class, the only long range force that we will work with is the gravitational force, and it actually will be present in every single example that we work with. So the gravitational force will always be present. All right, a force is a vector. So that means it has magnitude and direction. So when we are thinking about a force and we're doing our diagrams, we are going to use the particle model. So we're going to indicate our object with a particle, and then we are going to draw the force acting on the particle. We're going to put the tail of the vector on our particle. And then just like we've done with other vectors, the length of that vector is going to indicate magnitude. The direction is going to be the direction that the force is applied. So the direction of either the push or the pull. We also then can label, so it's a vector, so we can label that as some force with an arrow on top to indicate that it is a vector. Here I have three different situations. So I'm just going to do a quick little diagram showing where the forces are acting. So we're going to say these are all forces on the box. So using that notation from above, right, an object and an agent. So in each of these cases, so I'll just label these A, B, and C. In each of these cases, the object is the box. So that's the thing we're interested in, the forces that are acting on the box. So in each case, I want to identify what the agent is. So I'm going to make my box. I'm just going to represent that as a particle here. And so in the first one, the force that's acting on the box is the force of that rope pulling on the box. So I'm going to put this way. So this is going to represent the force. So the agent here is the rope. All right, so that's the thing that is contacting the box. That's the thing that is exerting the force is the rope. And so I could represent this force here as the force of rope on box. And so sometimes, especially early on, as we're thinking about our forces and identifying our forces, it's nice to be in the habit of saying, okay, what is the agent and what is the object? So we won't always use this explicit long notation here, but just recognize that if you see that force of something on something, so that's the agent on the object. And it just helps us explicitly recognize what the agent is and what the object is. So for situation A, object is the box, rope is the agent, the thing that is exerting the force on the box. If we look at situation B, so again, the object is the box. In this case, we have a spring. And I'm going to say this is a compressed spring, so that's not immediately obvious. So if I have a spring, I can have a stretched spring or a compressed spring. So we'll say this spring is compressed. And so if I'm compressing the spring against the box, again, this is a contact force. So the agent here is the spring. So that's the thing that's contacting the box. That's the thing that's going to exert the force on the box. And if we have compressed the spring is going to be pushing, again, the same direction that we had for A, right? The spring is going to want to go back to its equilibrium position. It's going to want to decompress, if you will. And so that force is going to go toward the right. So I could write this one. This is the force of the spring on the box. Right, again, using that agent and object notation. All right, in situation 3, we have a box, and this box is just supposed to be in free fall. So it's just falling through the air. So I'll just label that. So this is free fall. So if we have this box, so there's nothing contacting the box, but there is still a force. So we have that gravitational force. And the gravitational force is going to be pulling that box down. So our agent here, when we have the gravitational force, and we'll talk more about this in the coming days, but the agent here will be the Earth, right? That gravitational force is going to be an interaction between the object and the agent. So in this case, will be the Earth and the object that the Earth is acting on, which is our box. So we could write this force F Earth on box if we do that same sort of notation. Okay, so this is kind of the basics of how we're going to identify all of our forces. And one of the key parts of this whole next section is that we can identify the forces that are acting on our object and correctly include all of the forces and not put forces in there that are not real forces, right? That comes back to the idea of making sure every force has an agent. If there is no agent, then there is no force. All right, last thing I want to do in this video is just show that we can combine forces the same way when we first introduced working with vectors. So we can combine forces just using everything we know about our vectors. So in this picture here, so here I have another box. So I've got one force going this way, and I've got one force going this way. And we can say that our net force, right, is going to equal, so I'm going to just say F net is going to equal the sum of both of those forces together. So since they're vectors, we can just add those vectors together. So this is F1 plus F2. And just like we did when we introduced our vector addition previously, I can say that F net is also, if I put this in unit vector notation, F net in the x direction plus F net in the y direction. And then we know that that x component, F net in the x direction, is just F1x plus F2x, right? And F net y is F2x plus, wrong one, F1y, I'm in the y direction here, plus F2y. And so those are our component pieces. And so this is kind of the basis for a lot of what we're going to do when we're working problems in this section, where we're going to start with our second law. But we're going to think about combining our forces. And as we're combining our forces, we want to think about sort of isolating those forces in the x and y directions.